In this reading guide, we're covering 5.5, which is calorimetry. I actually stayed on the screen this time. Now let's go full screen. Okay, so we've got 5.5, which is calorimetry. And calorimetry sort of sounds like what? Calorie, right? Okay. Now, essentially, calorimetry is the process that they use. The reason that it sounds so much like calorie. This is actually the process they use to measure the amount of energy in the food that you buy at the grocery store. Okay? And so, and some of you have done labs like this probably in biology or, okay, so they had that lab in PBS last year. Okay, yeah, I didn't remember, or I didn't know if that was just in the new curriculum or if they'd had that in the old. It's still in there, yeah. But the idea is you take a piece of food and you burn it, and you see how much heat it gives off and how much it heats a certain amount of water, and based on the temperature change of the water, you can measure the amount of energy that is in that particular object. And that's what goes on the back of your cereal box or Cheetos or whatever it is that you're burning, okay? Now, some things are harder to burn than others. They have a very specialized device called a bomb calorimeter that they use to do this, okay? But that's the basic idea, and that's why it's called calorimetry, okay? I guess in this class we would probably more accurately be called joulerimetry because we usually measure energy in joules, not in calories. But for this, we'll kind of do both. So you have to be familiar with the calorie a little bit here, okay? And I guess one thing that's good to know about that conversion is that 1 calorie is equal to, let me make sure I get this right, because I haven't been getting things right today. Yeah, see, what I can never remember is no, it's 4.18, but I think that's right. I think a joule is smaller than a calorie, but let me make sure. Specific heat of water is 4.18 joules per gram degree Celsius, so yeah, that's got to be right, okay, because the specific heat of water is 1 calorie per gram degree Celsius. All right, so a calorie equals 4.18 joules, so there's your conversion for that one. So that helps you to get back and forth between calories and joules. Now that's something, excuse me, that's something that I would also expect them to give you on the equation sheet. No more mints. No, just cough drops. It was a subtle hint. There was only one. So, let's see. The main formula that we have in this particular section is Q equals C times M times delta T. So we got to talk about this for a second. Q stands for heat, right? Now, if you're doing your calorimetry at constant pressure, then you could also rewrite this as delta H is equal to C times M times delta T. That's supposed to be a triangle, not a teardrop. Q and delta H are the same thing as long as we are doing this at constant pressure, okay? Which the experiment we are going to do, the lab that we're going to do over calorimetry, is done at constant pressure, all right? So Q and delta H in that situation are one and the same, all right? Now C, we need to talk about a little bit. Anybody know what C stands for? I don't know why you would. It's not calories. It's specific heat capacity, which, what? We did not talk about that last year. So specific heat capacity is C. And all that basically means is certain objects have less of a temperature change when they absorb certain amounts of heat, just because of the intrinsic nature of their makeup. Water is one of those things that can actually absorb a lot of heat before it changes temperature. Can you give me an example of something that changes temperature rapidly as it absorbs heat? Say it again.
Copper.
Yeah, a lot of metals, right? That's why we cook with metal pans, because we want them to heat up quickly, right? So you don't have to add, I mean, just think about a pot on a stove, right? So you put the flame, if you got like the gas stove or even the electric, you put some heat on that pan, let it sit there for 5 minutes. Someone offers you $100 to touch the pan, or someone offers you $100 to just put your hand in the water. Which one are you going to do? Yeah, you're going to put your hand in the water, right? Because that water, 5 minutes after the beginning of the heat, probably hasn't started heating up nearly as much as the pan has, right? The pan has a lower specific heat. All right, so that's kind of the idea there. M stands for mass, okay? That's easy. And then delta T stands for the change in the temperature, okay? So if we know the specific heat capacity of the substance, we know its mass, and we know the temperature change, and this is pretty easy. We can figure out how much heat is gained or lost. Now, here's the typical strategy with these. Is there some way to hide this? Just put it down here. The typical strategy in a calorimetry is not to measure the specific heat capacity, the mass, and the temperature change for the substance that is reacting in the water. The strategy is to measure the temperature, the mass, and the specific heat of the water itself, because that's usually easier. Why would that be easier? Okay, I mean, usually we use water when we're doing solution-type experiments, right? But also, remember what we talked about the other day with the temperature thing, right? If we measure a temperature, what are we really measuring? Are we measuring the temperature of the system? If the temperature goes up, what is that telling us? Energy is being released by the system or lost by the system, right? So really what we're measuring is the temperature change of the surroundings, because the thermometer is part of the surroundings there, right? Okay? So the system itself, the thing that's doing the reacting, is releasing heat into the rest of the water. And that's really what we're measuring, is the temperature change of that water, okay? So that's what we do. We do a reaction inside this water, okay? But we are concerned about the specific heat capacity of the water, the mass of the water, and the temperature change of the water. If we know those things, that would tell us the heat either lost or gained by the water. Okay, but the water is the surroundings. That's around the reaction, but it's not participating in the reaction. Okay? So, if we find the heat of the surroundings, what can we say about the heat of the system? It's exactly the opposite, right? Okay, so once we find the Q for the water, we just change the sign, and we know the Q for the system itself. Okay, and that's usually the easiest way to do calorimetry. Does that make sense? Okay. Hang on a second. Oops, I hit the wrong button. Okay, so now let's actually do a practice problem here and see how this kind of works out. This is going to help you with the lab that we're doing in a couple of days, because the lab we're doing is a calorimetry lab. And I almost guarantee you there will be a calorimetry question on the AP exam. There was a big one last year, a big entire free response question on calorimetry. Okay, they consider it to be very important, which it probably is. So if you look at sample exercise 5.5, That's a pretty good example here of the type of question you might get asked. Okay? So that's on page 181, by the way, sample exercise 5.5, page 181. So A here is asking how much heat is needed to warm 250 grams of water, which is about a cup of water, from 22 degrees Celsius to near its boiling point, which is 98. The specific heat of water is 4.18 joules per gram times Kelvin. Okay? So we need our formula here, right? Q equals C times M times delta T. And what do we need to solve for in this one? Which of the variables are we solving for here? We're solving for Q, right? This is what we need to find. So we should have everything else. Now they gave us the specific heat, but what's a little bit weird about the way they gave us the specific heat? What are the units? Grams times Kelvin, right? They put a dash there sometimes. It really means grams times Kelvin. But the temperature was given to us in Celsius, right? Does that matter? Yeah, it sometimes does. When we're talking about temperature change, like a delta T, it actually doesn't, right? Because let's say our change in temperature is, it goes from 25 degrees Celsius to 50 degrees Celsius. Okay? That's a temperature change of 25 degrees Celsius. Can we agree on that? Now let's think about that in Kelvin. That goes from 298 Kelvin, right, to 323 Kelvin. Did I do it? Did I do mental math? Well, that's also a 25 Kelvin change, right? Because they're different, but they increase and decrease by the same increments. Okay? So when you're talking about temperature change, it actually doesn't matter. But if it makes you feel more comfortable, we can change it to 4.18 joules per gram times degrees Celsius.
Would it matter if it was in Fahrenheit?
Yes, it would matter if it was in Fahrenheit, because 1 degree Celsius to 2 degrees Celsius does not equal a 1 degree increase in Fahrenheit. There's actually a difference there in the way the scales work. Okay? So yeah, it would matter, but you're never going to see one in Fahrenheit because Fahrenheit's dumb. Right? We don't use Fahrenheit. So, so point is, you can change that unit if you want to, or you can change it to Kelvin if you want to, because our temperature change, actually maybe that's the easiest thing to do. Let's just change our temperature change to Kelvin. All right? So Q equals 4.18 joules per gram times Kelvin times our mass. What's our mass here? 250 grams. Times our change in temperature, which Celsius or Kelvin, doesn't matter. It's going to be 76. So we'll say it's a change of 76 Kelvin. Okay? That way our units match. And that's going to give us our Q. So you just multiply all of those together. Pretty simple. Um, 79,000, what's our sig figs here? Okay, the 250 grams only has 2 sig figs, and the temperatures only have 2 sig figs, so 79,000 joules. And it's just asking how much heat is needed to heat it up, okay? So that's how much heat we'd be adding into the system, right? Now, if the temperature was not increasing, if the temperature was decreasing, This right here would be a negative number. The 76K would be negative, which would make our Q negative. Does that make sense? Okay? But just in case you get a sign wrong somewhere up here, always check at the end to make sure it makes sense. Okay? We're adding heat into this system. That's endothermic, so this should be positive. All right? So that's how that works. That's part A. Part B, what is the molar heat capacity of water? Well, how would we figure that out? Well, I guess we'd have to talk about what the molar heat capacity is first. The molar heat capacity is basically just joules per mole. Okay? So, how would we get to joules per mole? Well, actually, I guess it's joules per mole times Kelvin, sorry. So if we use the specific heat, right, we've got 4.18 joules per gram times Kelvin. If we need to get to joules per mole times Kelvin, then we just do a little bit of dimensional analysis here. We need to get rid of grams, so we'll put that on the top. Put moles on the bottom. We're talking about water right now. So how many grams in 1 mole of water? 18. Okay. So you basically just take the 4.18, you multiply it by 18, and you get 75.2 joules per mole times Kelvin. So there's your molar heat capacity. Okay? Yes, ma'am. Are you talking about like up here? Yes, thank you for asking that. So up in the equation here, the specific heat equation, or I guess the calorimetry equation, because your specific heat is in joules per gram times Kelvin, you need to have your mass in grams, so that will cancel out. You need to have your temperature in Kelvin, so that those will cancel out, which leaves you just with joules. Okay? Yeah, they could give you a specific heat in different units. They could give it to you in kilojoules per mole times degrees Celsius, right? And if they gave you that, then you'd want to multiply by moles and by degrees Celsius instead. That would cancel out the moles and degrees Celsius, and it would give you kilojoules for an answer. Okay? So just always watch your units. Now, these are the most standard units they would give you a specific heat in. Is usually joules per gram times Kelvin. Sometimes you'll see joules per gram times degrees Celsius. Okay? Either way, it kind of works out the same, though, because the change in temperature Kelvin, change in temperature Celsius are the same. All right? If you need to go from Celsius to Kelvin at any point, you just add 273. And the way I always remember that, the lowest possible temperature you can get is 0 Kelvin. You can get a lot lower than that in Celsius. Yeah, the lowest, excuse me, the lowest possible temperature you can get is 0 Kelvin. I'm going to stick to that statement. Because negative Kelvin, they're actually higher temperatures, okay? So the lowest temperature you can get is 0 Kelvin, all right? And then degrees Celsius, you can get a lot lower than that. You can get into the negatives in Celsius, right? So that means Kelvin must always be a larger temperature than Celsius. So you'd have to add 273, all right? And then obviously going in the other direction, Kelvin to Celsius, you'd subtract 273. It's technically 273.15. As far as I can tell with the AP exam, 273 is just fine. Okay? All right. I think that, that basically covers the main stuff you need to know. There's a section in here about bomb calorimetry, which is not at constant pressure. That's not going to be the focus on the AP exam, all right? So you can look at that if you want to, but what we just did is going to be the main thing that you need to focus on, all right? Okay, we'll see you guys in class.